Hello everyone, my name is Gong Jia. I'm a third-year PhD student in the IST pillar ICT Singapore. Thanks for this opportunity. Today, I would like to introduce our CVPR 2022 work called MATTER. It's an active learning framework for human hand or body pose estimation. First is our motivation. Why do we need an active learning algorithm for pose estimation? Collecting a large-scale data set to train a pose estimator is expensive and time-consuming. This figure shows that we need to annotate multiple joints for each human body or hand sample, which costs around 30 seconds. Therefore, manually annotating a whole large-scale data set usually costs more than 100 hours, limiting the development of data set. One possible solution is to reduce the human efforts is active learning, which selects the most informative unlabeled images to annotate. However, it raises another problem. How do we select the most informative images for the pose estimator? As shown below, existing works can be categorized in the uncertainty-based or distribution-based method. However, the image selection strategies of this method do not directly related to the improvement of the pose estimator, leading to suboptimal performance. Motivated by this observation, we propose a reinforcement-based model to learn an optimal sampling strategy from data that directly maximize the performance of the target pose estimator. Next, I would like to introduce how to formulate the active learning procedure as a Markov decision process. The Markov decision process and active learning procedure are presented on these two figures. By comparing these two procedures, we can build the environment by the labeled pool and unlabeled pool and the pose estimator. Then regarded the sampling algorithm as the agent. In this scenario, the agent receives the state of the environment to take an action to select the images. Then the selected images is used to update the environment and then cause the state shift. Then the reward is the performance improvement of the updated pose estimator. In this work, we recorded the distribution drifts between the labeled and unlabeled pools on the future space to build the state. The design is based on an intuition that with an unbiased labeled dataset distribution, as shown in the figure B, the pose estimator is more likely to generalize well to unseen cases. Specifically, we build an appearance feature space and several topological feature spaces for pose estimation. The appearance feature records the characteristics of human body or hand shape and background. And the topological feature space recorded the global and local geometry information of the body or hand skeleton. Then the action is used to capture the potential contribution of the specific unlabeled sample when adding it to the labeled dataset. Here, the action consists of three components: the novelty of the pose in the image, the representativeness of the pose in the image, and the general appearance information of the picture. Finally, our reward is the difference in the pose estimator's accuracy on the reward set between this iteration and the last iteration. Then the pipeline of our MATTER is shown in the below figure. We first use a pose estimator to build the feature space to generate the state and actions. Then the agent team output the actions to select the unlabeled images to be annotated. Finally, we measure the reward on the reward dataset. Here we expanded one agent to another agent, to an agent team to achieve batch image selection. The motivation is that sampling a single image is inefficient. However, using a single agent to capture multiple images will lead to inferior performance. To select an informative image batch, we build an agent team module where the agents in the team sequentially select samples for annotations. And each agent can observe the previous agent's actions to perform the selection cooperatively, as shown in this figure. Finally, to demonstrate the effectiveness of our model, we conducted experiments on forwardly used pose datasets. Our model can save around 40% labeling efforts on average compared to state-of-the-art active learning frameworks. If you are interested in our paper, in our work, more details refer to our paper.